Hey guys, I just wanted to spend a few minutes highlighting some of the topics that you're definitely going to want to make sure that you look over for tomorrow's test. First is just a basic review of basic atomic structure. All right, we had worksheets such as this where there was a cartoon representation of a nucleus that showed protons and neutrons and electrons. Remember, you could figure out the element because the element is determined by the number of protons. All right, so in this case, this has 4 protons, so we could assume that it's, first of all, its atomic number is 4, and that would make this beryllium. All right, its mass, remember mass is the sum of the protons and the neutrons, so you just count up all of those there, so the mass of this one would be 9. All right, and then the charge has to do with protons and electrons. Remember, every proton has a positive 1 charge, every electron has a negative 1 charge. So whichever one you have more of is going to dictate the charge. So since in this case there's 2 more protons than electrons, its charge would be +2. All right, one thing I want to remind you guys about this cartoon representation right here is that it is very exaggerated. All right, this shows the nucleus much larger than it would actually be. All right, remember, if this were a real atom, the analogy is that the nucleus would be like a quarter sitting on the 50-yard line of a football stadium if the football stadium was the size of the atom. All right, so this greatly exaggerates the size of that nucleus. Recall also that atoms are commonly described using these atom symbols here, where you show the element. The lower left is the atomic number, all right? And because of that, the lower left is actually kind of optional, because if this is magnesium, this has to be 12 right here, for example. The top number is the mass number, which is the sum of the protons plus the neutrons. And then the top right is the charge. All right, so in this case, number of protons would be 12. Neutrons, all right, you have to figure out by subtracting this this number from this number, so that would be 13. And to figure out the electrons, you're going to want to look at the charge. All right, so what this means is that this particular atom has 2 more protons than it does electrons. So if it has 12 protons, that means it has to have 10 electrons. All right, that would be the ratio of, or the comparison of protons to electrons that would allow you to have a positive 2 charge. All right, make sure that you can do those both ways. All right, for example, this element right here, I could tell you that that is beryllium because of that number of protons right there. And you could figure out that the atomic number is 4. The atomic number, or sorry, the mass number in the upper left corner would be 9. That's the sum of these 2 right here. And then the charge, okay, so it's got 2 more protons than electrons, so that means it would have a +2 charge. All right, remember when you're drawing these, whenever the charge is either +1 or -1, you don't have to write the number. For example, when you just write it as F minus right here, then the charge would be -1. All right, here the charge is +1. All right, but you just write it as RB plus. All right. All right. Another thing that you might be asked to do is to show the calculation of an atomic mass for a particular element. All right. Remember that when you have an element, not all of the atoms of that element have the same number of neutrons. All right. And so what that means is some of the atoms are a little bit heavier than their neighbor. And so what you actually have on the periodic table is an average. It's a weighted average that tells you what the average atomic mass is for the atoms of that element. All right, so there's 2 things that you need to know in order to do that. First of all, you need to know the mass numbers of the atoms that are in that element. All right, so what this is saying is we've got this element right here, and there's 2 different varieties. One of the varieties has got these particles, one of the varieties has got these particles right here, and I can go ahead and say, I know that this thing right here is lithium, and this would be lithium 3. Sorry, not lithium 3. That would be lithium 6. And this one right here would be lithium 7. All right, and I can just figure that out by, in both cases, there's 3 protons. That means it's lithium. To get the mass numbers, you add up these. That gives you that mass number, and so forth. So in addition to knowing the mass numbers of these, you need to know the percentages that you have. And what this says is that this would have 7.51% of them would be this variety, 92.5 would be this variety. Notice how the percentages basically add up to 100%. All right. So how would you calculate the atomic mass? Remember, the general way of doing that is you do percent as decimal times the mass number plus, and then you do the same thing again, percent as decimal times the mass number, and so on. All right, and in this case, we're only going to do that for 2 because there's only 2 varieties right here. So the way this would work, 7.51 as a decimal is 0.0751. All right, you're going to multiply that by its mass number, which is 6. All right, the next one is going to be 0.925 times 7. All right. All right. We do the little calculations on that. That gives us this number right here. And the common procedure when you're doing mass numbers is to round to the closest hundredth. So I'm just going to round this at this position right here. All right, so don't worry about significant figures on these problems. Just round your final answer to the closest hundredth position. All right, so that would be this right here. So one thing you want to do is make sure that your answer makes sense. All right, so if we have 92.5% of this variety and 7.51% of this variety, there's 2 things that we know. First of all, our answer has to be between 6 and 7. All right, because it's an average of only those 2 varieties. Yep, it's an average, it's between those. Second of all, it's going to be closer to 7 because there's so many more of that particular variety. And notice how this is much closer to 7 than it is to 6. Okay, and so recall that that's what this number on the periodic table actually represents. All right, so you know what they do to figure that out is they figure out how many of each different variety of lithium atoms they have, and they do that exact same type of calculation that I just did right there. All right, you'll notice it's not exactly the number that they calculated. The reason that there's a little bit of a difference there gets into some concepts that are a little bit beyond what we'll talk about in this class, but you can see that it's very, very close. Okay, so remember to be familiar with the regions of the periodic table. All right, so there's a couple major divisions. First of all, basically anything over on this side, right over here, along with the ones at the bottom, those are all of your metals. All right, the only thing that you want to be sure of is remember hydrogen right here. It's in this column right here, and you might think everything on the left is a metal, but just remember that hydrogen is a non-metal, all right? So again, the non-metals are going to be basically everything over here, all right? All right, not including the ones that are in yellow there, all right? But hydrogen is going to be part of that, all right? And remember, a little interesting thing about hydrogen, on Jupiter, all right, if you put where there's a lot more gravity than what we have here on Earth, it's under so much pressure that hydrogen actually does exist as a metal. So it's not a total coincidence that it's in this column right here. It's just that on Earth, something having that is that light is not going to exist in its metallic form. All right. So metalloids. Metalloids are going to be the elements that go between them. All right. So the ones in yellow here are metalloids. Most famous example of that is silicon, which is used in semiconductors. That's where Silicon Valley gets its name from because there's so many computers made there. But just remember those kind of run between the metals and the non-metals. All right. The metals in this column are the alkali metals, We have the alkaline earth metals. We have the transition metals, which are the ones in this region that separates the two halves. We have the halogens right here. All right. Astatine would not be considered a halogen, but these top four right here would be. These are your noble gases right here. These are your inner transition metals. All right, so these are your transition metals right here, but your inner transition metals are generally printed outside of the main block. Notice that they would fit basically in this region right here of the periodic table. All right. One other thing that we need to know about the periodic table is trends. All right. So first of all, a little bit of nomenclature. With the periodic table, things that go up and down are considered to be in the same group. Sometimes you could call that in the same family. Things that are in the same row, going like this, are considered to be in the same period. All right, and remember, an easy way to remember that is that when you write a sentence which goes left right, you put a period at the end of it. And so if you see something that goes left right, just think period, and you should get it. So atomic size. All right, so this size. So even though we talked about comparing some things that were kind of where you had to use a little bit of logic, most of what you're going to have to know on the test are fairly straightforward. For example, comparing the size of two neutral elements. All right, so if I were to say titanium versus zirconium, which would be expected to be larger as a neutral atom. All right, so remember, atoms get larger as you go down, but they also get larger as you go to the left. All right, one way I think about it is just to remember cesium is the largest naturally occurring element. It would be francium, but francium is just too unstable to exist, so they can't really measure it. All right, so think of it as the thing that's the closest to this lower left is going to be the largest. All right, and when I say largest, a lot of times that's described as having the largest radius. All right, that's just a way of saying a bigger ball. All right, so between those two, zirconium would be larger. All right, if we had to compare chromium and iron as neutral atoms, chromium would be larger, all right, because it's farther left. All right, so we also had that size trend of an atom compared to its cation, which is its positive variety, and also a neutral atom compared to its anion, which is going to be its negative variety. All right. One quick way to remember that is that the more negative of the two that you're comparing is going to be the larger. All right. So if I had to compare chlorine neutral to chlorine minus, or Cl minus, Cl minus would be bigger. All right. So, but if I was to compare sodium to sodium plus, Na plus, the neutral sodium would be larger, because by comparison, something that is neutral is more negative than something that is positively charged. Okay. So there were a couple of other vocabulary words that we had in periodic trends. One of them was electronegativity, all right? And that was the ability for an atom to pull electrons, or sorry, for a nucleus to pull electrons towards itself, all right? The atom on the periodic table that does the absolute best job at that is fluorine. Fluorine is the most electronegative of all the elements. So again, just the closer you are to fluorine, the more electronegative. So if you go up on the periodic table, more electronegative. As you go to the right on the periodic table, it's more electronegative, right? Two other definitions: ionization energy, that's the energy required to pull an electron away from a neutral atom. Fluorine has the highest electronegativity. And electron affinity, that's the amount of energy released when an atom accepts an electron, all right? And fluorine also has the highest amount of that